Okay, now we'll review Chapter 8 by looking at some old test problems. Here's a typical Taylor series problem. Supposed to write the equations for a second-order Taylor series method. In other words, u at t plus h is u at t plus h times u prime plus h squared over 2 times u double prime. If you stop here, that's just Euler's method. The right-hand u prime is t squared plus u squared. And Taylor's second-order Taylor series method, one mixture term. For that, you need the second derivative, and you differentiate both sides of the differential equation to get u double prime. But remember, you're differentiating with respect to t, so u double prime is equal to 2t plus, what's the derivative with respect to t of u squared? Well, by the chain rule, it's 2u times u prime. Now, I would normally just leave this as u prime, except that it asks you to put everything in terms of u and t only, so you can go ahead and, if I were programming it, I would just say u double prime is 2t plus 2u times u prime, where I just calculated u prime, but now I explicitly plug that in there, and since it says to. Okay, the definition of order in Chapter 3 was different than in other chapters. In Chapter 3, the order meant error is proportional to power of the previous error, and that power is order. The higher the order, the better, because small number to a high power is very small. But for Chapter 5 and Chapter 8, order meant something else. It meant the power of h that the error is proportional to. And but it's essentially the same thing for quadrature methods of differential equations. So here's two problems that ask essentially the same thing, except that the error is not the error in approximating an integral, it's the error at the final point in approximating differential equations. But it really doesn't matter. If some error is proportional to h to the alpha, you solve for alpha the usual way. If you know the true value, true integral or true value of the differential equation at the final point, then you only need two tests, and you divide and m's go out and solve for alpha. But here's a case where you don't know the true value of the differential equation, the u of 1, the exact u of 1. So just like in Chapter 5, you had a problem in Chapter 5, Section 1, or Section 2, where you had to find the order even though you don't know the true integral, and you essentially have three equations and three unknowns. You reduce it down to two equations, two unknowns, divide out one equation, one unknown, solve for alpha. And that's exactly the same as in quadrature. It doesn't matter whether these errors are errors in a differential equation solver or a quadrature method, but it is different than Chapter 3. Here's a typical Section 8.7 problem. Reduce a problem to a system of first-order equations. If you had two equations here, one second order and one is third order, if you're going to solve it using any kind of standard software, it's probably going to expect it to be a system of 5 first-order equations. How do you do that? Well, the second-order equation, you reduce to a system of 2 first-order equations by defining u1 to be y and u2 to be y prime. And the third-order equation, you reduce to a system of 3 first-order equations by defining u3 to be z, u4 to be z prime, u5 to be z double prime. And this equation and these two are basically just defining the u2, u4, and u5. And the actual equations are here and here. u2 is y prime, so u2 prime is y double prime. u5 is z double prime, so u5 prime is z triple prime, and so we reduce it down to a system of 5 first-order equations. And notice on the right-hand side there cannot be any derivatives. These have to only be t, u1, u2, u3, u4, u5. No derivatives on the right-hand side. Here's a third-order differential equation. You're supposed to reduce it to a system of 3 first-order equations. Just define v to be u prime, w to be u double prime, so this will be u triple prime is equal to 5 u prime, which is v plus u plus t to the fourth. And then it says now write out Euler's method applied to that system. Well, Euler's method is just new vector UVW is old vector UVW plus H times F1, F2, F3. F1, F2, F3. So very straightforward once you have it written as a system of first order equations to apply Euler's method or other methods to it. Here's a third order Taylor series method. So we need U prime, U double prime, and U triple prime. U prime's directly from the differential equation, t times 1 plus u. You differentiate that to get the U double prime with respect to t, remembering that, what's the derivative of u? It's just U prime. And it's like I went ahead and plugged in U prime is t times 1 plus u, but I didn't have to. The U triple prime, take the derivative of that with respect to t, product rule 1 plus t squared times derivative of 1 plus u, which is U prime, plus 1 plus u times derivative of 1 plus t squared, which is 2t. And simplify that, plugging in what U prime is, and get everything in terms of t and u only. Here's another third order Taylor series method, but you're supposed to actually take one step with h equal to 0.01, starting with t equals 1, go forward to 1 plus h, where h is 0.01. So you need U prime at 1, U double prime at 1, U triple prime at 1, and h is 0.01, and you get this value here. Okay, some true-false questions relevant to Chapter 8. Disadvantage of the Runge-Kutta methods is they require several starting values. That's false. The multi-step methods require several starting values, but Runge-Kutta is a one-step method, so it's self-starting. It's easier to vary the step size for Runge-Kutta method than a multi-step method. That's true, because the Adams multi-step methods are assuming h is constant, and you have to interpolate, and it's a little bit of a pain in the neck to change h. Taylor series methods, so that's true. Taylor series methods are not widely used by general purpose ODE solvers because they require the user supply derivatives. That's true. That's their only problem. Normally a user doesn't want to have to take derivatives, just give, it's going to have to give f of t and u, but shouldn't have to give the derivative of that with respect to t. So they're not real popular, but they're stable and work well. Euler's method is equivalent to first order Taylor series method. That's true. Here's another problem where you reduce a system of two second order equations to four first order equations. Remember, there must not be any derivatives on the right hand side, only u1, u2, u3, u4, and then write Euler's method, and it's just new u vector is old u vector plus h times f vector.